SO2. So when we can close the this circle by having the step X, and the energy difference for the step X will be the formation enthalpy of SO3 minus the delta H of SO2. Why the minus? So if you go from SO2 plus half a mole and oxygen to sulfur and so on, we have to invert the arrow. So the direction of the arrow is important to know if you have to have a minus or not. Now, another pathway is, what about if we take SO3 and we prepare it starting from sulfur and oxygen atoms in the gas phase? So again, it has an enthalpy change that we don't know, but we can know it if we take into account things that we have from tables, like atomization energy from sulfur and the atomization energy of oxygen. In this case, 3 times oxygen, because it's 3 atoms of oxygen that we need. The other thing that we need is a formation enthalpy of SO3. And again, we have to invert the arrow, because we start from sulfur atoms, we go back to sulfur in the solid state. So that's the opposite direction. So it's a minus atomization enthalpy of sulfur. And the same thing for oxygen, but 3 times, because we have 3 atoms of oxygen. Here we have a third example. I will go a bit faster because I think by now you probably get the picture already. This is about formation of ethane, C2H6, from its elements in the natural form. That's carbon, which is solid, and dihydrogen, which is a gas. So there we can find the formation enthalpy of ethane, which is a given. So if you would want to know how much is the enthalpy difference if we start from the elements, we would have to atomize. And in that case, the same thing, we have to subtract the atomization to do that, because we're actually going in the opposite direction. So on. You could also then calculate the combustion enthalpy of ethane. And that's a process in which you combine ethane with oxygen. In this case, 3.5 moles of dioxygen to prepare 2 CO2s and 3 waters. So this is a reaction. And for any reaction, you can calculate the reaction enthalpy change, in this case Y, by taking the formation energies of the products with the right coefficients, and then subtracting from that the enthalpy changes of the starting materials, in this case ethane and oxygen with the right coefficients. These you can also find in table 4, these delta HFs. Okay, so again, I will stop screen sharing for a moment and see if we have any questions about that, if everything is clear. One thing I don't know if you have the availability of tables with the data, but at least I give you, let's say, the way to apply these Hess diagrams in a theoretical way if you would not have those data. Okay, at the moment see no questions. So again, I go back to the PowerPoint, and this. one more thing about thermodynamics. This is a more theoretical thing. We have seen that the second law of thermodynamics says that for a reaction to be spontaneous or to take place, the difference in entropy, the total difference in entropy, and that means the system plus the environment, has to be positive. It could also be formulated in a different way, and it says then that delta G of the system needs to be negative. So, and in fact, we can easily derive that, because in the first formulation, well, the total entropy change we can define as the one of the system and the one of the environments added to each other, and that has to be positive. So we can say that the environment will heat up, and this heat is the delta H divided by T. So we can replace it. It's still, the sum is larger than 10. Now, this heat that the environment has taken up is actually coming out of the system. So that means we can now look everything as based on the system. So that means there's an entropy change of the system minus delta H over T of the system. This has again to be larger than 0. Now we multiply everything by the temperature T, and then we see that we get a minus delta H plus T delta S of the system. That has to be larger than 0. If we multiply everything by minus 1, what we actually get is delta H minus T delta S is smaller than 0. And that's actually the same as the starting point that we have started. So that means delta G is negative if you have a spontaneous reaction. Just as an additional explanation. Okay, so that's this part. And I will go to another part in a moment. In the meantime, looking at the, let's see where it is, thermodynamics. Okay, I'm going to open it. Part 3, yeah. So here now we are doing some more calculations of thermodynamics before we arrive at kinetics, because we also have to do some stuff with kinetics. Okay, yeah. This is about a certain reaction that is very important in industry. The syngas generated from carbon and water. That happens at a high temperature. Water is a gas at that high temperature. CO and dihydrogen is formed. For our calculations, again, we can rely on data that are available in the literature or in tables, if you have them available. So now how do we calculate the thermodynamic units? And then later, how can we calculate the temperature domain in which the standard free energy is negative? In other words, when the reaction is spontaneous, if we take into account what we just have seen. Okay, so the delta H of a reaction, indeed, we just mentioned it, is the sum of the enthalpy changes of the products minus the sum of the enthalpy changes of the reagents. So I take the data from the tables and I arrive at a positive number of 131.3 kilojoule per mole. If I do the same for the entropy, I arrive also at a positive number of 133.9 joule. I put joule in red, not to make any mistake. Yes?
You are still at the camera screen.
Okay, I'm not sharing at the moment. I see. Then I will close that other things. Thank you for letting me know. So I close this and I continue then with the okay. I see. I will go out of it. Part 3. Yeah. Just give me a moment. Yeah, I'm not used to Zoom, eh? And so where is it? I don't find the screen that I need. Okay. How is it possible? Maybe I have too many things open and I should just close a few things. I think I'm going to open it again just to be on the safe side. Recapitulation. Okay, let's see if it works. Show all windows. Okay, yeah. I needed to scroll. So apparently I didn't scroll far enough. Sorry for that. This is a calculation of enthalpy changes. I will go a bit faster. So enthalpy changes, entropy changes, and then free energy can be calculated from that if you know the temperature. The data are taken from tables. So delta H was positive, 131.3 kilojoule per mole. Delta S was also positive for this reaction, and 103 point, but it's in joule. So keep into account that there's a factor of 1,000 between joule and kilojoule. So what is the temperature in which it becomes negative? So T delta S is going to be a negative number, minus T delta S is going to be a negative number because delta S is positive. So that means T delta S becomes more and more negative as T is increasing. At a certain point when T delta S is delta H, delta G is 0. And from then on, delta G will be negative. So we can simply calculate the temperature by making, let's say, just dividing 131.3 by 0.1339. Why 0.1339? It's in kilojoule. We put everything in kilojoule. So that means the temperature is 981 Kelvin, or if you want to express it in temperature Celsius, 708. So that means for this reaction to proceed spontaneously, you have to have a temperature of upwards of 708 degrees Celsius. So it's a very important industrial reaction, but you need high temperature. Okay. Yeah. So this is related reaction, also industrially important. It's about burning carbon with oxygen. Carbon is just like coal, it's a solid. And we can form different compounds, either carbon monoxide, and that we can consider to be reaction A. We can take more oxygen and prepare CO2. That's reaction B. Or CO can be oxidized and going to CO2. So these are three different reactions that can all occur. And in the same way as before, we can calculate the enthalpy, entropy changes, and also the free energies, if you want, at several temperatures. So, and for the energy of formation of the first reaction, we can see that it's a negative enthalpy and it's a positive entropy change. And so we can put that in one equation. So that means you, at the temperature 0, you have a very strongly negative negative enthalpy, which is of course not favorable. And then afterwards it becomes more and more negative. Now for burning CO to CO2, you see that the entropy change is actually very small. It's almost 0, 2.9. That means you now have a very flat free energy change. It's negative already quite strongly, but it hardly changes. In the case C, you have a negative entropy change, 173.1. So that means your temperature is not favorable, because you will actually increase your free energy, and at a certain point it will go above 0. So if you would put that into a graph, you would get something like that. And this is the free energy in function of the temperature. And so I put more than those three reactions, but you can see for some reactions, it more or less follows the line, a flat line. For others, they go down, others go up. And in general, if you have more gases after your reaction than before, that means you have a large positive delta S. And so in that case, you're actually going to go against the temperature, and you will go up, like in the purple line, for instance. So you actually decrease your entropy. So the slope is minus delta S of all of these different free energy equations. So here you can see how reactions with gases are influenced by the temperature, and it has to do with the free energy, and it has to do with the difference in entropy, which is the slope of the equation. Okay, so now I would like to say something about kinetics, but maybe before that I will again go out, and maybe you have some questions about it. So I hope now you could see the screen indeed. Okay, apparently everything okay. Yeah. So about kinetics, we will use the remaining half hour. It has to do with the rate of reactions, of course. That's and the rate of reactions we can describe in two different ways. You could say, okay, it's how much reaction products is forming in time, but you could also describe it as how fast is the reagent disappearing in the time. Important in kinetics is small k, the rate constant. Do not confuse it with a large k, which is the equilibrium constant that we will see in the next chapter. These are very different things, although one is related to the other. Okay, so we also talked about the order of the reaction. And the order of the reaction is, in fact, something that has to do with the influence that the concentration of the reagents has on the reaction rate. So first order means that the concentration is to the first power. So x is 1 in this case. Second order, you actually have to the square. So x is 2 and so on. So we actually discussed the two most simple kinetics, which are first order kinetics and second order kinetics. And this leads to two types of equations. The first order is the most simple. It's a logarithmic equation. And so that means if you would not use the logarithm, but you just look at concentration in function of time, you get the curve. That's the first graph that you see there. So from this curve, it's not so easy to make conclusions. If you take the logarithm, it's easier because now we get a straight line. And from this straight line, we can derive immediately a lot of data, like, for instance, the rate constant, because the slope is minus k, minus the rate constant. We can also use this curve to predict how much will be left of a certain compound after a certain time easily, because we just can extrapolate this curve. It's not so easy to extrapolate the line. I mean, it's not so easy to extrapolate like in the first graph, where exactly you will be there at a certain time. Now for the second order reactions, in order to have a straight line, you don't take the logarithm, but you take the reverse of the concentration. At any given moment in time, the concentration is A minus X, with X being the amount that has already reacted and A being the concentration in the beginning. So in that case, the reverse reciprocal of A minus X is 1 over A plus KT. So that means here we get a line that is going up, and the slope is K and not minus K in this case. We also discussed what means a half-life of a reaction. Now, the half-life of a reaction for a first order, we can calculate quite easily. It's ln divided by k, the rate constant. But in general, we can define half-life as the time needed for the original concentration to drop back to half. So instead of A, to go to A divided by 2. That's your half-life. And in a first order reaction, this half-life time is in fact a constant, because it's ln 2 divided by a constant. In the case of the second order, we have seen, it's not on the slide here, that the half-life is concentration dependent. So it's variable. It's not like for a first order reaction. Other things we have seen in kinetics are that a global reaction might have several elementary reactions. So steps that occur after each other. And that's part of knowing the reaction mechanism. And these steps energetically could be quite different. And depending on the energy, you could have rate determining steps. So what we see here on the slides is the reaction progress or reaction coordinates. And that's a non-scalar thing. That means just where are you in the reaction at a certain time. You start from the reactant, you go over the transition state to an intermediate, which is not the final product. The intermediate goes over a second transition state and finally gives the product. This is one example of a possible reaction profile where you have two elementary reactions. You can see step number 2 has a higher mountain. So the transition state is at quite high energy level as compared to the intermediate. So that's going to require a lot of energy. That's a big barrier, a bump in the road that will make it slower for the reaction to occur. So in this process, the second step is the rate determining step because it has the largest activation energy. We also talked about chain reactions where you have unstable intermediates like radical intermediates, for instance, and we talked about explosions, and these are chain reactions in which the intermediates multiply at every step. So that means your reaction is getting out of control. And finally, indeed, so much heat could be generated that you have gas and the gas expands and you have an explosion. One thing more that we discussed is about catalysis. Now, catalysis is a way to lower your activation energy, find an alternative pathway, and there are several ways to do that. You can dissolve a catalyst into your solution. It's evenly distributed, and then you talk about homogeneous catalysis. Or you could add a solid compound into a liquid phase, or you can lead a gas over a solid catalyst. That's heterogeneous catalysis. So you can see on the scheme here, again, it's an energy profile in function of reaction progress, and we go from reactions to products. In the green line, you can see this is the uncatalyzed reaction. You have a high energy mountain. This will be slow. It will be difficult. In some cases, even at a certain temperature, it's not possible to actually go over this mountain, and the reaction will be kinetically inhibited, you could say. So what do you do when you catalyze it? You could go over an alternative pathway. And in some cases, that involves having different elementary steps. For instance, here, it's not one step, but two steps. But you can see both steps actually have a lower activation energy. So that makes it easier because more molecules will have the required energy to go over the energy mountain, the activation energy, to the products. As you can see, the energy of the reactants and the products is not changing. So that means the same amount of free energy will be generated as a result of the process. So that's not influenced by the catalysis. Only thing that is influenced is the speed of the reaction. So at this point here, we have a number of questions which may help to understand this kinetics chapter. So we have the Arrhenius equation. Arrhenius equation, you can see here in the middle, that's K, the rate constant, is equal to a pre-exponential A, and this is multiplied by e to the power activation energy divided by RT. So the first thesis that we have here says that the Arrhenius constant A agrees with the value that K would have if all collisions were sufficiently energetic. So you could ask yourself, at which temperature are all collisions sufficiently energetic? This temperature has to be very high, or in fact, the temperature you could be seen it is close to infinity. Of course, if T is close to infinity, the term activation energy divided by RT becomes 0. What you have then is K is A multiplied by e to the minus 0. Any number that you have to the power 0 is 1. So that indeed becomes A. So this is a correct assumption. Indeed, A agrees with the value that you would have if all collisions are sufficiently energetic. But in general, of course, not all collisions are sufficiently energetic. So K will be smaller than A. And how much smaller, that depends on activation energy and temperature. Now, in B, it says that there is a relation between the Arrhenius constant A and the orientation of the reactants during a collision. Well, that's something that we have seen. We have talked about the steric factor P. And P is indeed nothing else than A. So you can relate the both theories, the collision theory and that of Arrhenius, to each other. And then what about the relation between the Arrhenius constant and the entropy of activation? I think also that we can prove, because we can relate the rate constant of reaction to the equilibrium constants, and equilibrium constant is something we will see in next chapter, of the reactants to the transition state. And that we can equal to the free energy over RT, again, something we'll see in next chapter. And that we can split in an enthalpic and an entropic term. And so delta H with this double cross, that's the delta H of the transition state. That's nothing else than the activation energy. And you can see this term we have also in the Arrhenius equation. K is A e to the power EA RT. So that means e to the power delta S over R is nothing else than A. So that means indeed there's a relation between the entropy of activation of the transition states and the Arrhenius constants. Here we have a small example of an exercise. I give this course also to pharmacy students. So this example is with aspirin. So it's aspirin is a drug, and it's metabolized, broken down, and this is in fact a chemical reaction. The chemical reaction is first order. We don't need to know any other detail than that. And we also know that the half-life time is 3 hours of this first order reaction. Now, it is asked to calculate how many milligrams of this drug, aspirin, would remain after 5 hours. And we take into account that the tablet originally contained 200 milligrams of aspirin. And we assume everything is taken up and so on. Okay, so we can solve this question because we know that a first order reaction has a constant half-life time. So we also knew it is 3 hours. So K can be calculated from that. So K is nothing else than ln2 over 3. And we can apply then the equation for first order kinetics. So ln A minus X is ln A minus 5K. So we have put the time as T is 5 in this case. So we put the K into that, so ln 2 over 3. So, and now we can calculate the ratio between what we have, A minus X, over the original compound. We just now have this factor 2 by E over minus 5/3. So we converted the logarithm to the base number in this case. So this factor is 0.378. So that is 1 minus the degree of conversion. So that's the fraction that is remaining. So if you multiply that fraction by the original amount, 200 milligram, we arrive at 75.6 milligram, which sounds like a reasonable number, knowing that after 2 half-lives, 6 hours, we normally should arrive at 1/4. That's about 50 milligram. So I think that is indeed reasonable. Okay, so there's another exercise. I'm just going out for a moment just to see if there are any things. So we have 8 minutes remaining. So maybe I still can do that one exercise. Huh? No, that's the wrong one. Stop here. No. What am I doing wrong? Ah, yeah, okay. It is the correct one, but I should go to. Yeah. Good. I'm back. I hope you can see this. So it's an exercise about a certain sample. So 10% of it has reacted in 45 seconds. So that means we have a fraction remaining that is 0.9. So we assume that the reaction follows first order kinetics. So how long would it take for the half of the sample to react? In other words, what is the half-life of this reaction? So for this to answer, we have to remember the equation for first order kinetics. So ln A minus X is ln A minus KT. So, and we know that the time was 45 seconds. We know that after this 0.9A, those 10% has reacted, is remaining. So we put that as A minus X. So now we can calculate K from that. If we do all of that, we can see that K is 2.34 10 to the minus 3 per second. And we need K, of course, to be able to calculate the half-life time, because we need to take ln 2 and divide it by the K that we just calculated. ln 2, that's just 0.693, and that means we need 296 seconds to do that, and that kind of looks, I would say, like it could be correct. So 10% is 45 seconds, about 50%, 296. I think that makes sense. So here we have an exercise about dinitrogen pentoxide. It's allowed to decompose. We again assume first order kinetics. It's in a closed vessel. We get NO2, nitrogen dioxide. We get dioxygen, O2. And we have the plot here in the graph. So, and this is typical multiple choice question, which is similar to what you could have at the exam. So the first one is which temperature can be assigned to which line? And then you would have to do a calculation for that. That's not multiple choice, to calculate the activation energy. So we have two temperatures, 35 degrees Celsius and 45 degrees Celsius, a higher temperature. So of course, K is larger for larger T. So the rate is always larger when you heat. So more conversion. So that means the line that goes down faster is the one at a higher temperature. So that's not a difficult question. The next one, we need an equation, ln A minus X ln A to minus KT, which can be also written in a different way. So if you have the two Ks, we have the two temperatures, we have the activation energy, everything is related to each other. We know T1 and we know T2. We know what is R, that's 8.31. So we need K1 and K2. So we can actually calculate that. From the same equation, K1 is 1.33, K2 is 5. That's about right, I think, because for most reactions, heating 10 degrees is about 3 times faster. So that is okay. So if we apply that, we put everything in, K1, K2, T1, T2, and R. The only unknown is activation energy. And in this case, we can calculate that the activation energy is 107.8 kilojoule per mole. We could also, if we know the activation energy, we could, for instance, calculate an unknown K if we have the temperatures and so on. So this is a very useful equation if you want to do kinetic exercises for first order reactions, of course. Okay, I think that's it for now. I'm going to stop sharing again. And we have a few minutes left for somebody said to move back to the previous slide. I must say I didn't see that. So could you say to me which slide that was? I think I have to. The previous slide, was that the previous slide here? Please remember that I can't see the chats. I think, well, I will try. Slide number 10, yeah, okay. That must have been it. So you have a question about it? So this is the logarithm of the concentration in function of the time. This graph, and you can see it goes down. That's to be expected, because more and more of the N2O5 will react. One graph goes down faster, and that's the graph at a higher temperature. And that's what I meant with it. And then the activation energy is indeed calculated from the data. And the data are in the graph 1500 and 1600s. And so is the time, I guess, in seconds. And then you can draw minus 2.5 and minus 3.1 as the logarithm of the concentration. And so these data you need 1500 and 2.5 to do the calculations. So you're right, I may have gone a bit fast here. So if you now go into that, yeah, here you see the 1500 seconds, for instance, at 308 Kelvin. So that leads to this. And then the other one, that's minus 2.5, and the other one was minus 3.1, I believe. And so we can do a similar calculation and then arrive at K2. So I hope that is helping. I think these files are also available if you want to look at it again. Any other questions? So the recapitulation slides are available to the teachers, so they can provide it to you. Okay, we move past our time. I'm still ready to stay here a few moments if some questions could come up. And, if not, I'm going to leave. In yes, please.
Do we have any reference book to practice and review the theory?
Yeah. This is a question for your docents. If they use any other reference books, you should address it to them. So what I provide are just the slides. Of course, we can discuss more in detail when I'm in Vietnam. Hopefully at the end of May. But I'm not going to make any decisions about reference books and so on. So these are provided by the local teachers.
All right, thank you, sir.
Yeah. Also, I referred to tables. So also those tables I made available to your teachers. If they're going to use them, they might make them available to you. But also there, I'm not making any decisions about that, because I'm not really 100% involved in the exercises that you get in between the classes. So I leave that to my local Vietnamese colleagues. Okay, looks like there are no further questions. In the meantime, my flight has been booked, so I'm looking forward to my upcoming visit to Hanoi and staying at your campus. So, and of course, it will be much easier when we meet in person to ask questions and to clarify some matters. Okay, see you, I think, for the third recapitulation, I think in 2 weeks probably. So bye-bye.
See you next time,
Bye,
Professor.
See you next time. Yeah.
See you next time.
Next time, Professor.
Goodbye, Professor.